Hi, in this video we're going to have another look at the lighting controller project. So I've written some firmware on the microcontroller now to do our trailing edge dimmer control. So it should drive this PCB with picking up the zero crossing waveform, so we'll get a little pulse every 10 milliseconds coinciding with 2 zero crossing points every full AC cycle. And then it can output a pulse width modulated signal to drive the gate driver on here, which will then drive the MOSFETs and then control the brightness of our lamp. It's also got a couple of inputs so that we can control the brightness with one of these buttons that's got the up and down control. And basically if we press up, we'll see the duty cycle ramp up to 100%. Press it once again and it will go right down to 0%. And if we hold it, we can adjust the duty cycle and thus the brightness to any level that we want. So this was causing me a little bit of trouble trying to use the built-in PWM module because it's not that configurable. You can set up a PWM frequency, but I wanted it to be quite robust, and I was trying to use some of the triggered modes for the PWM module. But basically, if the AC frequency was to shift slightly, there's no compensation for that, and it's possible that it would start glitching. So now, if I adjust the frequency, you can see it handles that happily. And if we lose the AC waveform altogether, there's just no gate drive whatsoever, which wasn't happening when I was trying to use the built-in PWM module. So this is a much more robust solution now, just using timers and interrupts, and it's really scalable, so we can drive as many outputs as we want without too much trouble. So I'm pretty happy with the firmware as it's running on this microcontroller now. So the next thing that we need to do is actually test the board here, and I've not power this up or anything like that, so I don't know whether this is going to work or whether it's going to blow up, but the first thing that we want to do is firstly check that we've got our isolation present. So we've got this isolation barrier here which is separating our extra low voltage electronics here from the mains on this side. So we've got these three devices, the DC to DC converter, and we've got an opto-isolated gate driver and then an opto-coupler for the zero crossing. So I'm going to get out the Fluke multifunction tester and we'll do an isolation test across the two sides. What I've done here is I've linked out all of the terminals on this side of the board with this piece of tinned copper wire, and then I've linked out all of the connections on this side of the board with the same type of wire. And basically what we're going to do is we're going to measure the impedance from one side of the board to the other, which is basically measuring the impedance through any of these three components together in parallel. So I've set the Fluke multifunction tester up to apply 1000 volts, and basically what it's going to do is apply 1000 volts across these two probes, measure the current that manages to flow between them through our circuit, and then basically you can infer the installation resistance from doing Ohm's law on that. Obviously the device does all of that for you. So we're going to connect one probe here and one probe across here, and press the test button, and you can see it's applying 1040 volts. And it measured an insulation resistance of greater than 1 gigohm. So we can be quite sure that these components are providing the isolation that we need, and that basically means that if we connect this up to the mains on this side of the board, even if we touch these bits with our finger, there's no way that we're going to get an electric shock. Right, so I've set up the boards to do some initial testing. So we're using the mixed-sig differential probe again, and that's being used to measure the AC waveform coming into the board. We've also got the Fluke 87 here measuring the current into the board, and the Fluke 179 measuring the voltage at the input on the board. So the differential probe is providing our safety mechanism for being able to probe on this side of the board without making our oscilloscope live at mains potential. And then on this side of the board we've not got our gate driver connected, and we've not got a lamp in the lamp holder yet. We've just got the 12 volt being supplied to this board, and we've also got the zero crossing connections onto here. And what I want to do is just make sure that we're picking up the zero crossing waveform correctly so that we're not firing the gate at random points in the AC waveform and creating loads of high currents in the MOSFETs and creating loads of noise. So we've also got our little switch here connected up so we can control the duty cycle. And the input here is also connected to the isolation transformer and also a variac, so we can ramp it up slowly and just make sure that we're not going to blow up the board. So we can turn on the power now, and we should be able to ramp up the voltage a bit. And you can see on the oscilloscope we're already starting to get our zero crossing waveform. So the yellow is the AC coming in, and the blue one is our zero crossing point on this side. So we're not drawing any excess current, so I'm going to ramp this up to 240 directly. Okay, so that all looks good, and if we control the brightness with the switch here, we should see the LED brightness go up and also the PWM waveform in purple on the oscilloscope. And there we go. So you can see on the oscilloscope we're effectively firing on the start of the AC waveform and then it's being turned off part of the way through, which is exactly what we want to do. It's the opposite of what we looked at previously with the leading edge dimmers. So that all seems to do what we need it to do. I guess the next thing we can do is connect up the gate driver wire, and we'll put a lamp in the lamp holder. Right, so I've just rejigged the setup so it's a little bit more clear and a little bit less cluttered around here. So we've got our mixing differential probe, which I did a video on in the last video. Links are down below if you're interested in this item. But it's connected between the neutral and this point here on the dimmer, so basically the feed into the light bulb. So we should see the chopped AC waveform. Unfortunately, I've not got two yet, so I can't look at the original waveform plus the chopped waveform, which is why two of these is really useful. I need to order another one. And then we've got the blue trace on the oscilloscope is looking at the zero crossing waveform on this side of the board. And then we've got in purple the gate trigger. So we should be able to increase the brightness on the lamp. It's already powered up. And there we go. So we can see our really nice chopped waveform on the oscilloscope in yellow. So basically we're on about 50%, and you can see the first half of the AC waveform. And then if we increase the brightness further, you can see we get our full AC waveform. And in contrast to my previous video, we're actually getting full brightness here, and we can also go all the way down to very, very low brightnesses. The lamp's not really lit, although it is drawing some current here, you can see. But yeah, we've got full control of the lamp over the full AC waveform, which is quite different to a lamp dimmer that doesn't have the neutral connection, because like I said, it needs to use some power in order to drive the gates and drive the electronics. So that seems to work pretty well on the incandescent light bulb, and yeah, it's giving really nice control here. So you can just turn it on, it slowly ramps up, turn it off, and there we go. So what we can do now is I've got another light. So here's the LED lamp that we're going to try out next. It's a Philips dimmable warm glow lamp, and it's about 8.5 watts. But you can see in there there's sort of a ring of LEDs, possibly. I'm not sure if you can see that yet. And then there's this really nice light guide which gives a really good coverage of light around the lamp. So these Philips lamps are really good. I really like those. Yeah, the lamp's cooled down a little bit now, so we should be able to put in the LED replacement instead. Right, so we should be able to turn this lamp on. And there we go, we're up to full brightness. And we're drawing significantly less current here. You can see it's probably about 10 times less than the 100 watt lamp that we were using before. And it's still just about as bright. And we should be able to dim this right down now. And interestingly, now we're at, what's the duty cycle? 13%, and the LED lamp is still illuminated. So on the dimmers that we tested in the other video, which I'll link to above, we weren't able to get these kind of low brightnesses with the lamp. There was always a minimum threshold because it needed some level of voltage across the lamp in order to turn on the triac. So we've got really good control. It's still lit up there. We can see we're drawing a small amount of current, and we're at 10% duty cycle now, and that's about as dim as it goes really. But yeah, we've got full control of an LED lamp with a really nice looking waveform. So you can see the cutoff isn't quite as sharp. When the gate gets turned off, there's a little bit of a slope downwards, and that's because this lamp is going to have some amount of capacitance in it, only enough to provide power for a very short period of time during the AC waveform, just for the switch mode power supply that's built into it. But there's a little bit of capacitance in there which we're seeing just as a slightly slower roll off on the AC waveform. Right, so I've hooked up half of the lab lights to the board. I've only done half to start with because this is going to be a really horrendous load for these MOSFETs. You'll see I've also put the snubber capacitor in here, which was missing before, because that is going to provide a small amount of leakage through from the phase conductor straight to the phase on the lights, but it should help with the edges slightly. But basically at the moment we've got 7 10 watt lamps. It's these N-Light sprites, but the ones that are in the lab are the 10 watt version, not the 8 watt. So this is going to be a really horrific load for the MOSFET. So let's see if it can control it. And there we go, it is managing to drive those okay. Yeah, so we're getting fairly decent control there. Let's see what happens if we hook up the rest of the lights. Right, so now we've got all 14 lights connected to the board, and I'm not sure whether the board's going to survive this or not. Normally when you buy one of these little dimmer modules, it says like 5 or 10 LEDs maximum, or a maximum wattage of LED lighting, and that's because each of these lamps has some capacitance in it, and that means that it's got an inrush current associated with it. So unlike your nice incandescent light bulbs that just look like a resistor, it's going to want to charge that capacitor as fast as possible when you first turn it on, which means that you see some really high peak currents through your MOSFET at the start of the AC waveform. So let's have a look and see what happens. So we'll try turning it on. And it is driving that okay. Let's try dimming it down. Yeah, I think we're seeing a few. Oh no, we've blown the MOSFETs there. So they're stuck on now, and we're trying to turn it off with the dimmer, but they're staying switched on. So it looks like we blew up those MOSFETs. It might be worth trying some bigger ones, just to see if it really is just the rating on these little MOSFETs that's causing it not to survive. Right, so I've put some bigger MOSFETs in here now, but actually I think what we were seeing before, I'm not sure if you noticed on the scope waveform, we saw some glitches occurring on the zero crossing waveform. And I think that was partly down to the fact that we've got these really long wires going off to the board, and any noise is going to be really easily coupled into these wires, because basically it's a 10k resistor with the opto coupler acting as an open collector transistor. So basically the impedance on here is 10k, which means it's going to be very easy for us to induce any currents in here. And I think what we were seeing was glitches mid-AC waveform, which then caused the MOSFETs to turn on midway through the AC waveform, and thus the capacitors and stuff in the LED lamps tried to charge really quickly, and we saw really high peak currents through the MOSFETs, which is what blew them up. So we've got the bigger MOSFETs in here now, and what I've done is just twist the wires together in an attempt to reduce the potential for crosstalk slightly, but we're not going to be able to really sort that out without having it all on one board, because this is completely non-optimal for this kind of thing. What I've also done with the differential probe, which is a really good thing about these differential probes, because it's completely floating, you can measure the voltage across any 2 points in your circuit as long as you're within the voltage ratings here. So what I've done is I put a 1 ohm resistor in series with the LED lights, and then I'm measuring the voltage across it. So on the oscilloscope, what we're actually seeing is a current measurement on the channel 1 waveform. So we've got a 1 ohm resistor, so that 1 volt translates to 1 amp, so we can do the conversion really easily. We've set the range to 50 times instead of 500 times on the differential probe, and what we should be able to do now is have a look at what the current waveform looks like for all these lamps. So let's turn the lights up to full. And there we go. So we can see the current waveform, and like I said, yeah, as soon as the power gets applied, you can see that rapid inrush current there, and then you sort of see it decaying somewhat following the AC waveform. And as we dim down, we're basically just seeing that later edge being chopped off. So it's behaving a little bit better than it was now, but you can actually see a little bit of a glitch on the zero crossing waveform. If you look at the blue trace, you can see a little bit of a glitch where we turn on the gate to the MOSFETs. So that's something that we need to address in the final circuit, just to stop the possibility of it triggering quite badly. But yeah, you can see we're drawing on the meter 0.75 amps RMS, and the peak that we're actually seeing on the oscilloscope is probably a little bit more than double that, so we're seeing almost 1.5 amps at the peak, and then it sort of decays away after that. So for me, this has been really useful in understanding the way that this circuit works with LED loads present, and it's clear why a lot of dimmer switches have a maximum load for LED lamps, because it's just going to blow the arse out of these MOSFETs if you have too many capacitive loads attached to the board. So what I'm going to do next is, over the next few days, I'm going to refine the schematic slightly for this, and I think I'll send off for some new boards. Firstly, that has everything all on one board, because obviously these long wires are causing us some issues. I'm going to refine the zero crossing detector, because this isn't the optimal setup, and it is also quite wasteful of power. We're dissipating basically all the power in these two resistors here, and I think there's a better way of doing that. And then we just need to eliminate the chance of any of those glitches occurring so that we can't damage these MOSFETs, and there's probably a little bit of software we can do there to try and help prevent that occur. So hopefully you found that video interesting. Don't forget to subscribe if you haven't already, and click on the bell icon so that you're notified of future uploads. If you are interested in buying one of these differential probes, I'll put the link down below. There is a discount code as well for Banggood as well if you're interested in buying from there. But until next time, thanks for watching.